happy to have Hung Tran, who will finish discussing periodic homogenization.
Thank you. Okay, before I forget, normally I should say this by the end of the class, but then I might forget. So let me start by saying that I really appreciate the time that Yifeng kind of Inwon putting into this summer school. It's a huge amount of time. It's the second time that I enjoy every minute in this whole week, and it's fantastic. I mean, I hope that all of you here have had a great time talking to people and lots of problems to come back and take. So thank you for all the effort. Seriously. So thank you. Yep. So we put a pressure on you that you have to keep it going. All right. So now I can start because otherwise I'm just gonna forget. All right. So I do it in a very backward way, that I start with general thing. I do vanishing viscosity. I do second order, and today I'll do first order equation. I will make some first results on the general settings. I mentioned certain sort of perspectives. It's going to be a bit heuristic and a bit philosophical. But right after the first 10 minutes or something like that, philosophical, I will go to prove something for you to add. Right. So let me make a remark that this is the ergodic problem here, right? This is defined in the torus. This is a first order equation. So remark is that the ergodic problem, EP, is a first order equation, right? Order equation. I said it earlier that it did count. So it also comes from KAM and weak KM theory. As noted that KM theory essentially because you start with a Hamiltonian depending on spatial and momentum. You hope that under change of variable involving V, you end up with the new Hamiltonian that only depends on the momentum, so that the trajectories, everything are straight lines. So you have integrability. So that's always the hope that to solve the Hamiltonian system, you have integrable systems. However, the difficulty stems in the fact that this V is not that nice, right? So the difficulty is always that you always have Y map to P, YP is only Lipschitz. In the spatial variable, it's only Lipschitz. Can have corners for sure, not smooth, and there exists many such V. So there can be many solutions to the cell problem, not one. So that's the first difficulty. The second difficulty is also quite severe, is that even though there are many such V in 2D or higher, there doesn't, in general, there doesn't exist a way to continuously select V. So to make it that P maps to B of YP is even continuous. In order to do serious rigorous change of variable, you need to have differentiability in a lot more properties. So the difficulties really stems on that fact. So that's why first order equation is quite difficult. Still, there is a very fundamental result. So again, historically, that as I described to you, qualitative theory was done by Lyons, Papa Nicolau. Baradan and Evans around 87, 89. And then quantitative theory. It took some more times to get to quantitative theory, and the really fundamental result was done by Capuzzo-Donchetta and Ishii. This was done, I think, around it's published in 2001, but maybe done a bit earlier. So this very fundamental result that they proved that for this conversion, we have U epsilon minus U in L infinity. I mean, it's not written exactly like that, but in the modern way, not modern way. It can be formulated like this in written in my book, C times epsilon to the 1/3. So this is a very fundamental, important result by Capuzzo-Donchetta and Ishii. I'll explain to you roughly, very briefly, how they did it. And after this result, there are many new papers afterwards following their method and generalized to various different settings. For example, you saw in Seho's poster that he also got epsilon to the 1/3 this year for the Hilbert space setting, so for infinite dimensional setting too. So it's a very very good framework. You see, it took 15 years or so to get to this result. And when they got this, it was not even known whether it is optimal or not, right? So I view all of this quantitative theory or everything like this is not an end result. What I view is it's a means to understand deeper and better about the solutions, right? I mean, to get there, we need to derive and understand better properties of such. And so let me tell you just a brief idea of how they overcome the difficulty, right? Because you see, this is not even continuous, right? So the earlier asymptotic expansion that I wrote down for you guys was U epsilon xt would be approximately equals to U xt plus epsilon v of x over epsilon evaluated at the vector p, which is du of xt. So this was the earlier heuristic. And you see that if I were to do the analysis, I would need to have very strong dependence here, right? So it doesn't work like that. So the idea by Capuzzo-Donchetta and Ishii is that they say, okay, I really don't have the nice thing about the corrector. Then I should pull back, right? As analysts, if you don't have nice things about something, then you might consider its approximations, right? So the brief idea here is that they, instead of looking at EP, they look at the discount approximation that I explained to you earlier, lambda v lambda yp plus h of y dv lambda of yp equals to 0. So earlier I proved to you that as lambda goes to 0, we have convergence. And in fact, if you do it carefully, what you have is that you would have lambda v lambda of yp converge to minus h bar. So plus h bar of p is less than or equals to c times lambda. That's the first thing that you have. The second thing that you have would be that, in fact, you also have that you don't have Lipschitz here for v, but for v lambda you have its Lipschitz. However, the Lipschitz constant blows up. Okay, so you would have v lambda of y P minus V lambda Y cube less than or equal to C over lambda times P minus V. Okay, so it's Lipschitz, but blows up. It's natural, right? If it's not blows up, then something wrong. So you would have that P maps to V lambda Y. P is Lipschitz with Lipschitz constant C over lambda. So it blows up. Yeah. So I mean, you know, by now it's very standard, but they realize that instead of using this one as test function, they're gonna use this sort of V lambda as a replacement, but at the cost of this lambda factor that you have to pay. Okay, so they would do some sort of replacement. Again, this is sort of a little bit philosophical because I'm not exactly write out the proof for you, but they would think about this U epsilon xt is approximately equal to U xt plus epsilon V lambda x over epsilon evaluated at like what we talked about yesterday by doubling variable at the U xt. Okay, so by balancing the parameters, they're gonna choose lambda is equal to epsilon to the 1/3 or something, and there's the other parameters you have to balance, and then another parameter to balance. Basically, you have three parameters. So at the end of the day, you have epsilon to the 1/3 because you have to balance three parameters together. Okay. Now again, it's a little bit philosophical because I'm not doing the computation for you, but at least I want to explain to you how it went. Okay. Yeah. So if you really want to do it, let me write down for you in case you want to go back home and try. Yes.
The equation for choosing lambda equals third.
Yes. Okay. Yeah, that's right. Okay, I'm writing it down.
Oh, I didn't miss it.
Yeah, you don't miss it. Okay. So epsilon V lambda x over epsilon. Here I have to do the doubling variable. I would need to do it like z minus y over alpha plus x minus y squared plus y minus z squared plus t minus s squared over alpha or 2 alpha or whatever minus k. There's another parameter. Okay. Epsilon. Well, epsilon to the 1/3. I'm a little bit lazy at this point. I'm writing it like this. Okay. Yeah. So you see that there are three parameters here. There's epsilon is here. I would have lambda. I would need to choose it to be epsilon to some power alpha, and then alpha is bad. Epsilon to the power theta 1, and I have alpha here. I would need to choose it epsilon to the power theta 2. So when I balance things out, the best way to do it is just to choose both of the parameter to be 1/3. Yeah, that's how they did it. Okay. If you have to write down, so that's exactly my point. Everyone was wondering about this. I talked to Hitoshi Ishii many times. It's like, you know, is it seriously optimal? We have doubts. We were curious about this, and we were always wondering, like, maybe there's a way to do it better, right? The way was just to choose it like this. And in fact, we have conjectures. In the paper written with Hiroshi Shimitake and Yifeng, we conjecture in 1D, the rate is 1/2. And then afterwards, I made a bolder conjecture that the optimal rate in general is epsilon to the 1/2. Okay, but it turns out that my conjecture was wrong. Okay, so yes, I'm just yeah. So there's a new theorem. I don't have time to do it, but I'll explain to you a little bit why. So there's a theorem that we just proved. We just posted this week, so that I can explain a tiny bit about that. So this is with Jiung Zhang, he just left because he has to catch an airplane. With Chi Sun, and we're moving to Rutger now. And with Yifeng, we prove the following, that in 1D, the optimal rate for general convex, non-convex setting, we have that in 1D, the optimal rate is epsilon to the 1/2. Okay, so in 1D, our conjecture is correct, it's 1/2, because we don't have a lot of space, we have to have rigidity. In 3D or higher, surprisingly, we didn't believe this. That we thought that there's something not optimal here, but we confirmed that the result by Capuzzo, Chata, and Ishii is optimal. So the optimal rate is exactly epsilon to the 1/3. I'll explain to you, because related to this, when we introduce an example to confirm this, we have 3 parameters. We have to balance it out. And then in 2D, the optimal rate is epsilon to the 1/3, but up to some log corrections. Yeah. So let me explain to you again philosophically, because I don't have time to go to this. What the example is like and why in 3D or higher the rate is epsilon to the 1/3. Because again, I first thought that it's non-convex setting, this corresponding to 2-person games, right? We have differential game between 2 persons, so only 2 players playing. So, 2 players, right? So it should be 1/2. But it turns out that we realized now that there is a very sort of like heuristic explanation of epsilon to the 1/3 in 3D. And we sent this paper to Hitoshi a couple of days ago. He was excited. He was like, yeah. Anyway, he was very happy because it's confirmed that the rate they got is optimal. So this confirmed the rate optimal in Capuzzo and Chata and Ishii. So here is the explanation of epsilon to the 1/3 in 3D. So here's how we do it with Yifeng, Jiung, and Qi, is that we look at how players play games in 2D. Eventually, when we write out the proofs, it's sub and super solutions. But let's fix a radius. Let's say in our paper we fix a radius of 1/3, and we look at 2 players playing game by sort of like messing around the circle. So one player is gonna choose vertices of a regular polygons along a circle. But let's say that the first player choose vertices. Okay, too many. Okay, the first player choose some nj vertices of a nj regular polygons. Like this along the circle, and the other player also choose nj vertices but of a interlacing nj regular polygon. So just there, because in order for the players to kind of mess up with each other, they have to sort of be interlacing in the between. So something like this. So the other one is also do nj vertices. Okay, let me denote the scale. I use Alpha is roughly 1 over nj. Is alpha j is our scale. Then because the two players are playing game, right? They one want to maximize certain things, the other one wants to minimize certain things. And when we take the differences, you know, roughly speaking, it's gonna give you a scale. I mean, if you take the differences, for example, you can define, okay, how to see the differences. For example, I can define, maybe the best way is to write down something like this. Let's define alpha 1, alpha is bad. F1 of x is a function which is supremum of x dot with the vector. Let's call this one, I have a name for it, but let's vertex is v1j, v1j. Okay, for j running, not j, v1I for 1 less than equals to I less than equals to j. So that's corresponding to the first player, and I have the second player f2x is supremum 1 less than equals to I less than equals to j, x dot with v2j. Okay, so those are v2I, v2I. v1I, v2I. So when we take the differences of the two players, what we see is this one. So f1x, I'm about to get to the point that Inwon has. What we see when we take the differences, this is roughly speaking, is of the order of magnitude of the length of x dot with alpha j squared. So alpha j squared here comes from what? Comes from the projection. If I take one of this vertex and the other one, I project this one down. I see the difference. So alpha j here, square here is roughly speaking 1 minus cosine alpha j, if I did it correctly. I think so, right? Yeah. Okay. So roughly speaking, I have alpha j squared. So I have two players. So those give me two scales. Okay. But what we realize is that there's still this x parameter in the game, because x can grow, right? Because the trajectory can grow. So eventually what we learned is that alpha j here coming square here coming from two players. And this is again very hand wavy. I'm just doing scaling. But however, we learned that there's still the x parameter here that is, when we compute, is roughly speaking of the length of alpha j times t, where t is the time the game goes. So as a result, when we combine things together, we have the relative scale. We see alpha j cube times t is roughly speaking of order 1.
So do you use the game representation?
We have the game representation in our mind. You can read the paper we just posted this week. It's written in a very simple way, just a couple of pages that just we define everything by this kind of geometry, and to compute we just use super solutions. So no gap. But I'm trying to explain to you the scales that we see. Roughly speaking, those 2 points are competing with each other, so it's kind of two-player games. Okay, so we have this scale, and also you see in the students' presentation yesterday, they did realize that t here is the time you have to go to see homogenization scale. So t is 1 over epsilon. So you see then alpha j is epsilon to the 1/3. So this confirms the Kapuzan-Jetta issue result. Again, this is very hand wavy. I'm not proving anything. Okay, but at least that. Okay. Disclaimer. Indeed, this Chi-Sun run ChatGPT 5.6. We did get help from ChatGPT. It's very complicated. It spits out lots of files. Nonsense, but it helps us to find some intuition. Eventually, we wrote down all the construction by ourselves. But when Yifeng and I saw it's in 3D Higher, it confirmed. First, it confirmed that maybe this is correct, but as the dimension goes to infinity, we thought that it might be wrong, but we sat down and checked. And we, as I said, I learned a new dimensions here because we learned this new scale limit, and I will need to think more. It's a beautiful interlacing game. So people trying to play with each other with this kind of scaling, very elementary geometry. Okay. All right. So at least again, this is philosophical for the experts in the room. Well, now let me get to some proof that I want to prove for you guys. So the theorem 2 I want to prove for today. So this is confirming that surprisingly that in the general non-convex setting, we have conversion rate. Optimal is epsilon to the 1/3 in Higher, 3D, 2D or Higher. The question is what happened in the convex setting, right? In the convex setting where the Hamiltonian is convex, right? So let's say I assume further that P maps to H of YP is convex. So I want to give you the proof on this today. So this is a theorem by Yifeng and I a couple of years ago that we proved that the optimal rate is epsilon. So optimal rate is O epsilon. So we do have U epsilon xt minus U xt is less than or equal to C times epsilon for all xt in Rn cross 0 infinity. So we have the conversion rate. And even at this moment, we are very puzzled because in non-convex setting is epsilon to 1/3, in convex setting is epsilon. There's a gap, right? I mean, spectrum gap or whatever between 1/3 and 1. We are still thinking, and we have to figure out what's filling in the void. Okay, so very briefly about the literature, because there are people here in the room that are also involved. So before what we did this, we got this result. We have an earlier paper with Hiroyoshi Mitake that we use Wickham theory and others to get some first result, optimal one-sided bound, and some other results. And then afterwards, there's a Cooperman sort of use our optimal control framework and use first pass speculation to get to near optimal. And after this is done, there's a huge flow of results sort of using this framework to have it done for many other settings. For example, in the case with boundary, there's a result by Mitake, Pandruni, and also Jiung Zhang and Yusi Han, and a lot others. And then recently there are also some results in the infinite dimensional setting for in the Wasserstein space by Jian Ding, Ibrahim Akran, okay, Dulce Han and Antonio Zichidis, Michigan and Purdue, and by Seo Park here for the base of the Hilbert space with the rearrangement invariant. So lots of development. It turns out that this framework is quite robust. So I'm going to tell you this framework is simple enough to tell you. Okay, so let me tell you about this framework. Okay, so how to get O epsilon. Okay. So let's start. I'm gonna assume that you know the optimal control formula. If not, you can just accept it. I will write out the optimal control formula for the solution of U epsilon of xt. This is infimum. I'm just gonna write down first. Gamma t equals to x. of the action functional. It's come from calculus operation, integral from 0 to t, L, the Lagrangian of gamma s over epsilon, gamma dot of s, ds, plus initial data g of gamma 0. A picture here in case you have not seen it. So this is the point xt. You try to go from the point xt backward to any given possible point. Okay. So this is gamma 0, 0. So your value, this is the so-called value functions, is the minimum, is the value going, minimum cost going from any given point here to the point xt. So it includes, this is a so-called running terminal cost, and this is a so-called running cost, right? If you have taken PDE, graded PDE, that is in chapter 10 of Advanced. If not, you can just assume that this is given to you. Okay. For the sake of to make it simple, I'm gonna assume G is equal to 0 for simplicity. Okay. I'm even assuming G is 0 for simplicity. Okay. I want to tell you this because at the end, I want to tell you another open problem that is related. So I mean, you know, most of the problems I tell you, there's also problems concerning mean curvature flow. It's different from what Yan explained, because I'm looking at, you know, whatever I'm looking at here is more like large scale average. So I look at global problem, and I'm scaling it out. Okay, so that's U epsilon, right? So because we assume we assume G equal to 0, we have the simple version U epsilon xt equals to infimum of gamma t equals to x of the integral 0 to t L of gamma s over epsilon gamma dot of s ds. Okay. I am uncomfortable with this slot because it's oscillatory, right? But as you know, we have done multivariable calculus or whatever. If I have this highly oscillatory scale that I don't like, I can do to change a variable, right? To get rid of that, so I can do a change of variable. If I'm not mistaken, I can write at I'm always having trouble with this. Epsilon r is equals to gamma of r over epsilon. I do this change of variable. Wait, did I do it right? I think so. Wait, what? No. See, gamma. Oh. Okay, let me write differently. So I let gamma s equals to epsilon eta of s over epsilon. Okay. Then I have gamma dot of s would equals to eta dot of s over epsilon, right? So I can get rid of this one. So if you do that change of variable, what you ended up with is you have infimum. I would have epsilon eta of t over epsilon equals to x of the integral now becomes, you know, you do that change of variable, you have epsilon times integral from 0 to t over epsilon L of eta dot of r, sorry, eta dot of r, r. Okay. You have the free ends, right? Because, you know, you have this formula. Right, simple calculus of variation problem, right? If you stare at this formula for some minutes, what you realize is that actually you are doing large time average here, right? You are doing ergodicity, quantitative ergodicity here. You integrate for a long time and you take the average. Makes sense. So that's what I meant. If you see homogenization is exactly large time average. You want to do it quantitatively. Okay. So this is a very simple object that you have seen, right? This is just a basic object from calculus of variation, right? How much does it cost for you to go from X to Y in a time, let's say T, right? You can define this object. We call it a metric functions because it's essentially a metric distance going in time T from X to Y is infimum of gamma 0 equals to X, gamma T equals to Y of the integral from 0 to T, the action functional, L of gamma S, gamma dot S, ds. Okay, this metric distance. If you define this metric distance, then your problem becomes exactly infimum of epsilon eta of T over epsilon X equal to 0. Equals to X. This one is nothing but the metric distance going in time epsilon times T over epsilon going from any point. Okay, so let's say Y over epsilon to this point, which is X over epsilon. So this is infimum of YRM. It becomes this problem. So you go for a large time, you average it out. Okay, so that's a problem. Yeah, so the problem becomes quantitative lifetime average of the metric distance, metric function. Yeah, I'm calling it a function now to make sure that we are not mistaken. I mean, this is roughly a metric distance, but sometimes we don't have symmetry and blah blah blah. But does that make sense? Right. Okay. So now let me even simplify more. Right. I'm gonna fix a directions, and I'm gonna do with you. I'm gonna. Okay. So another simplification. Because everything is shiftable, right? So I'm just gonna look at the limit as epsilon goes to 0 of epsilon m. I'm gonna fix t is 1 and 1 over epsilon going from, let's say, y there. So this is 0 going to z over epsilon as epsilon goes to 0. I'm just gonna look at this one. So say a vector z is fixed. Fixed with bounded. So I'm even just gonna look at this limit and see how it goes. Once I can quantify this, I can do some a priori estimates and some finite speed of propagation and put this one by. It's not a problem. So it's just a basic quantitative estimate. Yeah. So let me tell you. Let me draw this picture and tell you how this is, and also it's actually indeed. If I consider event, I'll try to do it on time so that I'll recall to you the two front propagation problem I tell you. The first front propagation problem, it turns out that this corresponding to the averaging the Riemannian distance, periodic Riemannian metric, as time goes. So, okay, let me write down the problem. The question we care about is a fix z be a bounded vector. I look at the limit as epsilon goes to 0 of epsilon m 1 over epsilon 0 z over epsilon. If you feel uncomfortable with this, you can do a change of variable. You let epsilon equals to 1 over k. You write like this, and it might look more familiar with you. You let k goes to infinity, 1 over k m k 0 to kz. So you are really doing quantitative ergodicity, right? You want to quantify what's the ergodic limit as, so let's say this is the direction, the direction of the vector z. What it asks is that, let's say you go from 0 to kz, where k is far away. Let's say that, okay, maybe this is a unit cell. This is a unit cell, y equals to 0, 1 to the n. So your geodesic corresponding to this, this gives you a minimizer or geodesic, right? Your geodesic is going in a long run from here to kz, right? As k goes to infinity, it's along that direction, right? Remember, everything is periodic. So if you look at this picture, this one is being pulled back to the unit cell to be this, to be this, to be that, whatever. So eventually, what you're doing, if you shift everything back to the unit cell, meaning that you have your geodesic visiting some parts of the torus, and you want to average it out, right? So it's exactly ergodicity. Does that make sense? Right. Sometimes you might not see all the torus. It depends on the problem. Yeah. So the theorem that we prove, and with this theorem, we can get the results that Yifeng and I prove, is that we prove that there exists a limit m bar, we call it m bar. Okay, in this case, it's one homogeneous, doesn't matter, 1, 0, z, such that what we see is 1 over k m k 0 kz minus m bar 1, 0, z. This is less than or equal to c over k. So we prove that the conversion rate is exactly 1 over k, which is epsilon. So does that make sense? Yeah. Okay, so let me tell you, how do we prove this theorem? Okay, that's good enough. So some key ideas how we prove this one, and I want to show you that this is actually doable without time. What we have is that the key idea is, what we prove is that we have some observation first, right? Observation. The observations are actually good enough for us to prove one first claim. The first observation I have is that I have the triangle inequality. Because this is essentially a metric distance, right? So going in time t plus s from x to z is cheaper than going in time t from x to y, and going in time s from y to z. Right? Going in x to z is cheaper than going from x to y and then y to z. That's obvious, right? It's just by definition. The second thing that we have is the periodicity. Yeah, and actually, let me write that. And some of you did ask me that is periodicity important? So going in time t from x to y is equal to going in time t from x plus k to y plus k. But k is being an integer vector. It's also, both of them are obvious. So periodicity or certain ergodicity, like stationary ergodic or randomness, is important because we need them in order to see the repeatedness, right? We need them. We need to have repeated structure so that we have the limit exists. So those are the two obvious things. And from them, what it gives us is an important property for this limit is the subadditivity. So this is one of the first key idea. So the first key is the first key idea, which is the subadditivity. Subadditivity. Subadditivity is essentially triangle inequality. Subadditivity means that I have going in time 2 from 0 to 2z is gonna be cheaper than twice going from in term 1 from 0 to z plus the constant. So that's some additivity that we have. Okay. So let me give you a picture proof of this, and then I'll go to another one. Okay, so picture proof of some additivity. Well, I mean, what you see is that essentially you need to go from 0 to, this is z, this is 2z. I mean, like, let's say going from 0 to z, I have already a geodesic, right? Like this, right? So to create a geodesic going from 0 to 2z, essentially I just need to make 2 copies of this and glue them together, right? Not quite, because I cannot just shift this one for any vector, but I can shift it for integer vectors, right? I mean, I can shift it for integer vectors. So let's say that this vector z is not quite an integer vector, right? But it's close to some integer vector. So let's say that maybe z is in this shifted cell. This is something y plus some integer vector k in k is now whatever q. Yeah, I'm out of z to the n. Okay, so what you can only shift by an integer vector, so you shift it like this to this. Okay, then you have to do certain, you have to pay certain price to connect. You know, you go like this, and then you have to save some time, and you connect from here to here. You save some time, you connect from here to here. That's results in this constant. Okay, you have to pay certain price. You have to do it carefully. Okay? Yeah. So and you might see that, you might say that, okay, but this is not exactly subadditivity function that you have seen, right? Because there's this constant c here, but you can always add a constant. So c is the cost to connect the mismatch, the mismatches, right? And then you can subtract everything by c, m20 to z. Wait, I'm sorry. Plus c is less than or equal to 2 times m10z plus a constant. So you can always do basic analysis to add them, so it becomes a subadditive function. Okay, and there's a fun thing. This is called Fekete lemma. This is what I like to give when I teach baby routine. If you have not done that, you can have fun. You'll have to consider a function f mapping from can be the whole line, but n is okay. N to well, let's take the infinity, where you have f of k plus l is less than or equals to fk plus fl. So it's subadditive, right? Additive means equal, then it's kind of like subadditive meaning it's always bending down, right? Because it's always bending down, you can easily have you can prove this for fun, you know, if you cannot sleep on your airplane when you're flying back. This is a c is infimum of l greater than or equals to 0 fl over l. Basic fact. So this subadditivity is the key of all problems concerning like first pass speculations or stochastic homogenizations, is that when you have subadditivity, you have existence of I mean, if you do only qualitative result, this is it for stochastic homogenization or for first pass speculations. When you prove the limiting shape exists, that's it. Okay, so this is enough. However, this only gives us one-sided bound, right? So, oh yeah, actually, let me show you another thing that is fun from here. That what you can get is you get one-sided inequality from this bar. Okay, so what do you have? My time is okay. What do you have? What do I want to do? I want to prove this inequality, right? Yeah, so from here, sorry, yes, so from here I have 1 over k, m of k0, kz, plus a constant, it doesn't matter. Okay, let's say that I do have already that it converges to m bar of 1, 0, z, right? I already have this inequality as a conversion. So let me prove from subadditivity, I claim that we have one inequality, right? How do we see it? We, see it just basically everywhere from everything is already clear. Okay, so how do we get one-sided inequality? Let's look at m k0 kz plus a constant. You have seen, right? This is less than equals to 2 to any power m, m 2 to the m, wait, 2 to the j, m 2 to the j, 0, 2 to the j, sorry, m 2 to the j times k, 0, 2 to the j times z plus c, right? By induction, I just do it to make it 2 to the j. Okay, I already have this inequality, and then I just divide and obtain the result. Very simple. So if we divide, did I say it right? Yes, we divide, so we have 1 over k. Something is wrong. Something is wrong. Yeah, I'm sorry, I flip it. This is greater than equal 2 to the j times this. Right? So I have this. So I divide by 1 over k times 2 to the j. I have 1 over k m of k0 kz. I wanted to give you a proof of this so that you see that in fact it's not hard. It's quite clear what's going on. 1 over 2 to the jk, m 2 to the jk, 0, 2 to the jkz plus a constant c, it doesn't matter. This converges to exactly m bar of 1, 0, z, right? As j goes to infinity. So I have this inequality, right? So I have 1 over k, m k 0 kz plus c is greater than or equals to m bar. So you see that subadditivity not only gives you conversion, but gives you one-sided inequality. Okay. So what is missing that earlier it took us a long time to see, right now it's very obvious. Well, is the second point, second key is the so-called superadditivity. Okay, by now it's obvious that we proved that m the other way around 2, 0, 2z plus c is greater than or equals to 2m 1, 0, z. So superadditivity, it goes the other way. In other words, we prove essentially that our metric distance is essentially linear within a bandwidth of a constant, right? So in a bandwidth of constant like that, your function is kind of within, essentially, right? So linearity gives you exactly the conversion rate. So here we use we need to use the so-called curve cutting lemma. I will state it. I'll give you a picture proof of superadditivity, and I think I need to start to give you a final discussion. Curve cutting lemma. This is due to, okay, to be fair, this is suggested by Fidia Nazarov, suggested to Burago, and Burago and Perelman give the proof. This was before they moved to the US. This was before Perelman started study the one correct or maybe I don't know. Independently, it was studied by Noga Allen in combinatorics, and there's a weaker result. These two are equivalent. There's a weaker result by Alexander in first passes percolation with a log error term. So all of them popping around at the same time. They didn't talk to each other. They didn't know each other. Eventually, we were the one that discovered that they were all related. But this is fun. I mean, this. The paper is only by Burago, but it's suggested to Burago and Nazarov, and this proof is given by Burago and Kernman. The curve cutting lemma, I'm just gonna write down that if you have a curve, if you have a curve gamma going from 0, 1, this is a basic topology statement to Rm that's continuous. And the proof is by using what? By using Borsuk-Ulam theorem. Okay. If you have a curve gamma mapping from 0, 1 to M that is continuous, and there exists a number k, capital K less than or equals to M plus 1 over 2, and a collection of k disjoint intervals A1, B1 up to AK, BK of 0, 1, such that you have the total displacement I from 1 to K, capital K. Of gamma BI minus gamma AI is equals to half of the total displacement. So it's an analog version of the intermediate value theorem in higher dimensions. The intermediate value theorems in one dimension tells you that to go from 0 to 1, you must go to 1/2, right? In higher dimensions, this is wrong for a curve if you don't cut it in many pieces. So the simplest way that I can give you is this example. You take a curve going from 0, 0 to 2, 2. But this is your curve. This is your curve. Going from 0 to 2, 2. Okay. What you see is that surely it doesn't go through the middle, right? Yeah. If we, again, teach baby Rudin, we talked about baby Rudin yesterday, right? So if we teach about baby Rudin, there's a session telling you that the intermediate value theorem falls for continuous curve. It doesn't go to the midpoint, right? However, that was because we think about it too rigid, in a too rigid way. You have your curve that has a lot of degree of freedom. You need to give yourself more degree of freedoms, more pieces to cut, right? So I think this is an important point where research too is that you should not be too rigid, right? So the suggestion is simply that, yeah, it doesn't go through the midpoint, but let's cut it into 3 pieces. I cut it halfway here, So my curve is cut into 3 pieces, right? The first one and the third one in total is exactly halfway, right? You see? And the middle one itself is this one, right? The total displacement is exactly halfway through. So So yeah, I think this, as I said, this lemma should be in real analysis. Unfortunately, the proof is using Borsuk-Ulam theorem, so it's a bit of fun. Okay, so I don't have time, so let me finish the proof now. I don't have time to give you the proof by that Borsuk-Ulam theorem, but it's in our paper. Yifeng and I, we have a lecture notes on Wickham theory on our website. You can check. The proof is very cute. Okay, so now let me give you a picture proof. prove superadditivity. It's also very simple, but then I want to address to you that the implications. So superadditivity now is that I need to go, I go from 0 to 2z, I have a geodesic. Let's say this is my geodesic from 0 to 2z. Surely it doesn't go through the midpoint. However, I can cut it into some pieces. Let's say I cut it into this piece. I cut it into this piece. So these two pieces together, okay, this is wrong, but yeah. This piece. So these two pieces together joined from 0 to z, and the other piece together joined from 0 to z. Okay, again, this is bad, but okay. Anyway, so I would have that m of 2 going from 0 to 2z. I can cut them into two pieces, right? I pay some price because I have to do the connector. Then I can make them into two pieces going from 0 to z in term 1. Does that make sense? Then I'm done, right? Okay. So now let me give you the conclusion. And one more open problem in this aspect is that, yes, so finally at this moment we do have optimal conversion rate for both non-convex and convex cases, but there's still a gap in the between that we don't know what to do, right? But even for the convex case, there's something that I think that this sort of tool is developed, but there's something missing that maybe we can develop further. So the conclusion, I want to go back to the two examples I gave you at the beginning. To start with is that we have the first example. First example is a so-called front propagation where the velocity v of x is equal to a of x times a unit normal. Okay, that's my first example. Now let's assume that a is C2 periodic. Okay, assume a is this. And now I look at my initial front. I call this one gamma 0 is the unit sphere, or you can say the set U enclosed by gamma 0 is a ball, right? And look at my initial front, and I do front propagations. So things propagates out. Depending on my velocity v is a times n, right? Just propagates out. Everything is periodic, so it's at some time this is ut enclosed by gamma t. This is us enclosed by gamma s. Okay, based on the theorem we just proved, in fact, we have the limiting shape. This is exactly first passage populations. I have the limiting shape as t goes to infinity of ut over t is going to be equal to some shape called u tilde at this limit. And further, we have proved that the distance between this quantitative term is less than or equal to c over 2. Okay, that's the result. And again, I don't have time to go deeply into this, but this front propagation problem, in fact, is corresponding to the Riemannian metric dx squared over I x squared or something. I might be wrong. I think so. Okay. So we are looking at a periodic Riemannian metric, and we look at as time goes, the shape is getting bigger and bigger, right? And then we average it out. We have this u tilde. At this moment, to this day, the question about the shape, what is the shape of u tilde? How does it look like? Is still very open. Does it have corner? It's convex. Does it have corner? This is, I think people call it limiting shape, or what is it?
Waffle.
Wolf shape. Yeah, wolf shape. Yeah, right. So, but I want to address finally one open problem. I think it's really important. I have been thinking about that, but I don't have any idea yet. It's back to the mean curvature problem. So this is an open problem. I mean, this is also an open problem, but it's too vague, right? I mean, well, it's a big open problem. But the open problem is I look at the front propagation problem, Vx equals to Ax minus kappa n, right? And again, I start with the set U0 is B0, 1, and gamma 0 is the boundary of U0. So you now also do front propagation. You start with U0, which is a unit ball. You propagate things out. But there's a curvature involved now, right? So everything propagates out. So this is gonna give you UT and gamma T. So if homogenization holds, then you do have that the limit as t goes to infinity of ut over t does exist. It's equals to u2 as well. The question is, what's the conversion rate and what can we tell more? Right? I mean, Inwon does this for, I mean, if you take each of the front is planar, then it's clear, right? Here I'm looking at all directions, so it propagates in all directions. So what's the rate? Optimal rate.
It has like flat parts sometimes in any of these.
Yes. Yeah, it's a big open problem. Yes, yeah. That no in 3D. There's a paper by Burago, Ivanov, Kleiner. There's some understandings about yeah, but still pretty hard. Yeah, that's why this is a big to me is a very important problem. Actually, maybe sometimes you don't need to know what the shape. Some cutting, some mechanism, shift things around might work. And to end that, I think that it might related to a paper by Cafrali de la Labs that people have been telling me. I have not been able to do it. That they wrote a paper. I mean, it's kind of more like minimal surfaces, right? But there can be relation because they consider. Anyway, it's vague, but I think that this is important. Again, it's a mean to understand deeper. It's not the end, right? You know, that's how I view it. Okay, thank you.
Any more questions for him? Yes.
So this might be super naive question, but you mentioned how in the convex case, the scaling is like epsilon, and in non-convex it's epsilon to the 1/3, and there's a gap there.
Yes.
Do you suspect that there's some intermediate strength of assumption like pseudo or quasi-convexity that would give you a different?
Yeah, very good point. So in the paper we posted this week with Yifeng, Jiwon, and Chi, maybe if H is quasi-convex, there can be something in the between. I don't know. So this is why I view that it's sort of really interesting because like we keep wondering about it every day. What is happening? Why 1/3? I mean, like I'm still.
Will you explain to us?
Yes, mechanism, but I'm still not fully satisfied. We are still wondering every day. Even at least we are still debating.
Right. So the point is like for convex case, get a capital epsilon. Philosophically, you have the asymptotic expansion. Right? But to make rigorous, they can make them story. But for non-convex, it's philosophically why is 1/3. That's complete mystery. Like from each, what they did is the pure PD methods, and they balance those parameters. You get 1/3. Back then, no one believed that it could be optimal because there are a lot of like tight inequality there. There's no reason why be optimal. But just miraculously, just as Fang said, like with the help of ChatGPT, like to come up with this miracle example. Actually, it's exactly 1/3. But again, why? Like this is how Hunt explained this. Like you have geometry because it's approximation of the circle, the second order, then get 1/3. So one thing is from this approximation geometry 1/3. The other one is from the PD 1/3. How exactly these two things could match exactly? So that's a complete mystery.
Yeah. We need to understand more. Because if you look at the naive expansion is epsilon. But you can see that yesterday I proved that in the general second order case, this expansion is not correct. The rate is square root of epsilon. And in the first order case, it's epsilon to the 1/3, which is kind of weird, right? In the convex setting, this picture explains why it's epsilon, because everything is within a bounded width, right? So there's only one scale. But you can see that in the non-convex setting, what we first thought, and I was quite confident when I posted that conjecture on my webpage, was that there are two players, so they can only control two scales. Then we learned that by interlacing, not only they control two scales, but they control also the scales of x equal to ct. So how much it can propagate. Here because it's bounded width, so it has to propagate with order t. But there is only the propagation speed. There was only x, which is alpha j times t. So it can slow things down. So because two player, it's also clear, right? I mean, heuristically, you're messing up, arguing with each other. So you cannot go with constant speed. You keep arguing. You have to slow down. So what we learn is that because we have to keep arguing, we can only go to t to the 2/3.
Yeah, I mean, maybe there's some properties of H that you can somehow put into the constants, and maybe something with.
Yeah. That I don't know. So yes, so there's just indeed that we want to solve this mystery more. Okay. What's the gap between 1/3 and 1? But clearly you can see what I'm telling you here is it's in that example, it slows things down. It's only going to this point. Here it's going order t. Here it slows down. And as I said, arguing, I argue with family, then maybe we're gonna drive slower. I don't know.
More questions?